Okay, welcome. This is class day 14. I'm going to cover, finish up chapter 6. We've got a little more to do, and then I'm going to introduce chapter 7. So first, let's look at the syllabus. This is the video for Friday, September 23. And we should be on chapter 7, and we'll get there in just a few minutes. I'm just going to cover a few things on chapter 6 that we didn't cover on Monday, and then I did the video for Wednesday because I forgot to do the class. But this next Wednesday we will have a class live and in person, and I promise to show up. Okay. So I want you to make sure you are keeping up with the homework and the quizzes, so stay on top of that. And all right, here's the book. So this is chapter 7, and the idea then is to learn how to use K-maps. And so there's some terms. So before we're done with this, I want you to absolutely understand what is an implicant, what is a prime implicant, what is an essential prime implicant, and what are the non-essential prime implicants, which generally we call consensus terms. And I think pretty much all non-essential prime implicants are consensus terms. All right, there is a video right here. And you should watch that video at some point. I guess it's just kind of a bonus video. And so if you remember the two-variable truth table, and we just map the boxes in like this. If you look at the K-map, the boxes, each row, remember each row in the K-map we number. The top row is 0, the next is 1, 2, and 3. So in a two-variable map we have 4 rows, 0, 1, 2, 3. In a three-variable map we have 8 rows, 0, 1, 2, 3, 4, 5, 6, 7. And in a four-variable map, we'll have 16 rows, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You're welcome to do, instead of 10, 11, 12, 13, 14, 15, you can say A, B, C, D, E, F. Okay, so you need to know how to map these things from the truth table into the K-map. Now, in this two-variable K-map, there's no flipping of rows or columns. In a three-variable, where we always are going to do it in this orientation, we have to flip these rows. So notice the bottom two rows we have dash and little dash, and they go in opposite order. And then the first column, we start with row 0, 1, and then the next one, the min-term for 2, or the desired value for f, goes in the bottom box for 2, and then for 3 it goes in the box 1 up from the bottom because we flip these rows. And the same on this. So the boxes are numbered 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7. Now sometimes it picks up the cursor and sometimes it doesn't. And so in case it didn't, in this case, what I'm going to do is, let me just do that again on paper, just to remind you. So here we have a three-variable map. Now you can definitely do a three-variable map in this direction with A and B on top and C down the side, just one variable on the side. So we just have 2 rows on the side, and we have 1, 2, 3, 4 rows across. But we're never going to do this. We're always going to do them vertically, like this. It's totally equivalent. Doesn't really matter. It's just what you get used to. Okay. But I'm going to always do them this way, just because it's a little confusing. So I don't want confusion. So we're going to put A across the top and BC down the side. Now remember our alternate labels. I guess I should do this up like that. Okay, yeah, that's fine. Yeah, there we go. Okay. All right, so this column is A, and this column would be A prime, but I'm not going to write it because it gets too cluttered. The bottom 2 rows are B, and the middle 2 rows are C, which means the top 2 rows are B prime, and the top row and the bottom row are C prime. Okay, and this is how you can read things off the map. So if I pick a box, say this box right here, then I know if it's a single box, since it's a three-variable map, it'll be a three-variable term. Every box by itself will be a three-variable term. So this would be A, B prime, C. So this box would be A, B prime, C. And this box down here would be A prime, B, C prime. This would be A prime, because it's in the A prime column, B, because the bottom 2 rows are B, and C prime, because the bottom in the top row are C prime. So A prime, B prime, C prime. All right, we number these 0, 1, and then we have to flip 2, 3, 4, 5, 6, 7. And if we do a 4 variable map, so we have 4 columns and 4 rows. We do A and B across the top now, and C and D down the side. So we have A and B across the top, C and D down the side. We call the rightmost 2 columns A. We call the middle 2 columns B. The bottom 2 rows we call C, and the middle 2 rows we call D. So the variables just slide around because now we've got 2 variables across the top and CD down the side. All right? And so if we pick a box, say right here, that is going to be A, B, C, D. So this one would be A, B, C, D. We're almost off the page. I can't even read it. Sorry. Okay, so you get the idea. All right, so this is really important. In a 4 variable map, we number the boxes 0, 1. We still flip these bottom 2 rows. 2, 3, 4, 5, 6, 7. That's identical to a 3 variable map. But then we go on. Now we flip these columns. So from 7 we go to 8, 9, skip 10, and back here 11, and then here 12, 13, flip these, 14, and finally 15. Okay? And of course row 15 is going to be A, B, C, D. And row 0 is going to be A prime, B prime, C prime, D prime. Now when we have groups, then we can look at them and we can read them off. Now one of the things that's a little bit tricky to do, your eyes give you this information right off the, just once you train yourself a little bit, your visual system automatically does some of this work for you. So it's really helpful and important to train your eyes to do this, and your visual system is pretty good at it. So you don't have to work too hard to get trained up. All right, what is a little bit tricky? Let's say I have a group of 4 right here. Being able to read that, or maybe I have a group of 2 right here, or maybe I have say a group of 2 right there. So I have 3 groups. Now I'll put a 1 here instead of a don't care. Okay, so how would I read these off? Well, you should be able, in this case, you should look, you see, because we have 4 boxes, you're going to drop 2 variables. If you just have 2 boxes, you're going to drop 1 variable. So this group of 2 is going to be a 3 variable term. And this group of 2 is going to be a 3 variable term. This, however, group of 4 is going to be a 2 variable term. And how do you read it? Well, so I know that the variables that change are dropping. So I know I have C down here and C prime up here, so C is going to drop. And I know I have B in the middle 2 columns and B prime on the outside 2 columns. So I know B is going to drop. So I'm left with A prime, which are these 2 columns, and D, which are the middle 2 columns. So this group is A prime D. That's A prime D. Okay? And this group of 2, I know the middle 2 columns are B. I know over here is A and this is A prime, so I know I'm going to drop B. I'm going to drop A. So then I'm left with B, and I know this whole row is CD. So it's just B, C, D. And then this group of 2, I know it's going to be A. B is going to be 0 here in this column and 1 in this column, so B is going to drop. And I know C and D are both 0 up here, so that's going to be, it's going to be A, C prime, D prime, and the B's gone. All right? So it's always good to identify which variables are dropping. Once you get rid of them, you see what you've got left, and that defines your min-term. Now remember, if you're doing the max terms, the zeros, then what you do is you pretend they're 1s, write it like they were 1s, and then invert it because they're not 1s, they're zeros. So for instance, what if we had 2 zeros here? Well, so instead of did I write this one down? Yeah, A, C prime, D prime, B, C, D, and then A prime, D. So the original map would be this. What if these were zeros? Then we'll say everything else is 1s, so I'll put 1s everywhere else. Okay. All right. So that term, what would that term be? Well, we said it was A, C, D prime. So if we pretend, okay, I'll pretend those are ones. If they were ones, it would be A, C prime, D prime. And now I just invert this, and that gives me my max term, which turns out to be A prime plus C plus D in parentheses, because it's going to be multiplied by the other max terms. All right? So, and then you cross this out because it's wrong. If these are zeros, this wouldn't be correct, because you don't want a min term when they're zeros. You want a max term. So you have to pretend they're ones, write what it would be with ones, and then just invert it. That'll give you the correct max term. You can do it directly in a max term if you want, but I know that tends to confuse me a little bit. If I do it this way, I always get it right. If I do it the other way, I make mistakes. Okay. Well, I can make mistakes even if I do it this way, but I do better. All right. Okay, so let's moving on. So you should definitely read through the chapter, and so we'll progress to this is a 3-variable map. Here's our desired f. Now remember, every 3-variable map, every 4-variable map has a defined min term and max term for every row. But of course we would never include all the min terms. We only include those min terms where the desired value for f for a particular row is a 1. And then for that particular row, we do include that min term. And when we included all the min terms for all the rows where f is 1, we have the solution. The same in the K-map. When we have a K-map, so let me plot. So we'll take this truth table. I'm going to draw the K-map right now, and then we'll come back and we'll work on it. Okay, so I'm drawing it. You see. Okay, now I'm gonna plug in the values. So note in this chart that we have. So what are the min terms? I'm going to write them down. So we have min terms 0, 1, and then we don't have 2 or 3, and then we have 4, 5, 6, and we don't have 7. All right. So now let me transition. And okay, so we have min terms 0, 1, 2, 0, 1, 4, 5, 6. Okay, and I'm only going to write in the ones. I'm not going to write the zeros in. So 0, 1, 2, 3, 4, 5, 6. So this is going to be a nice little group of 2, and this is going to be a wraparound. We don't want to do this by itself. We want to combine it with this box up here, because this box, all the wraparound boxes count. So the bottom row is considered adjacent to the top row. All right. So again, if we do our alternate labels, this is A, this is B, these 2 bottom rows, and the 2 middle rows are C. So what do we have here? Well, so we have C and C prime, so C is going to drop. And we have A and A prime, so A is going to drop. So we're just left with B, but it isn't B because it's B prime. So this is B prime, and then we're going to add to that this group of 2. Now, since we combined 4 boxes, we drop 2 variables, so we're just left with B prime. But if we have 2 boxes, we drop 1 variable, and that 1 variable we're going to drop. So we know this whole column is A. We know this is B here, but that's B prime up here, so the B is going to drop. And we know this is C prime and C prime. So this group of 2 is going to be A, C prime. So our final solution is B prime plus A, C prime. And that's the answer, okay? So B prime plus A, C prime. Now, if we wanted to convert that to SOP, well, we could use switching algebra. It would be really easy. We just use conversion theorem 2, the second distributive law. We let this be x, that's y, z, and we have b prime plus a quantity times b prime plus c prime. Normally we'd write that a plus b prime to keep it in alphabetical order, make it easier to read. That's the SOP. And if we look at it, we see that that's the POS. So this is SOP form, this is POS form. We could also do the same thing if we put in the zeros. So if we put in the zeros, we got one group here, and we have one group here. Now it's perfectly okay to use this 0 twice. Now how do we do that? I first pretend they're ones, write it if they were ones. If they were ones, A would drop, so I'd be left with BC. So I'd write BC, then I invert it, then I get b prime plus c prime. And then this group of 2, so we have a prime. If they were ones, we would have a prime and b, a prime b. So now I invert that, and I get a plus b prime quantity. So our final answer is a plus b prime, or b prime plus a, however you want to say it, and b prime plus c prime, just like we started out. All right, so that's how this works. What I want you to do is draw some maps, do the homework, draw some maps, and do some practice so you get good at reading these values off. It really will help you if you do a little practice, and you can use K-maps with some degree of ease. If you're struggling with them, then you'll have trouble. So make sure you work with them. All right. Now, okay. So let's do. So I think what I'm going to do. Let's see. Yeah, let me go through the slides. So I'm going to do these. Let me set this up. Hang on. Okay, so here are the slides, and so we'll go to where we got to already. So remember that we can use it for 2 variables, 3 variables, 4 variables, or 5. 6 is kind of hard to do, and we haven't really covered the 5 and the 6. And then maybe we'll work some problems. Okay, so let's remember, for every time we combine boxes, we're basically using the fact that they differ by a single variable, which is this theorem: x y prime plus x y equals x. And now, of course, the x part of this could be a b c, and the y prime could be d prime, and this could be a b c, and the y could be d. So you'd be left with a b c. The d would drop. Okay, so we use this, and we also use the corollary, which is x plus y prime quantity times x plus y equals x. Same idea. Okay, so remember, there may be multiple equivalent solutions that are different, and we call those equivalent or equivalent solutions. All right. All right. So we did 2 variables, we did 3 variables, and now I want to get to 4 variables. All right, this is good. So here we have I don't show you the truth table, but what do we have for minterms? We have minterm 0, 1, and then 2, 3, 4, 5, 6, 7. So we have minterms 0 and 1, 5 and 7, and we can cover this map with these 2 groups of 2. We don't. That's all we need. We've covered all the ones. But we can also add in this other term right here with the dash line, the blue dash line, and that is a consensus term. So this group of 2 is a prime, b prime, c prime. This group of 2 is a prime, b, d, and this consensus term is a prime, c prime, d. Now, we sometimes do want to add consensus terms when we have a hazard, and the consensus term will often fix the hazard. So we always want to keep that in the back of our mind. But we don't really have to have it to cover all the ones. So we may or may not include the consensus term, depending on the problem and whether or not a hazard is popped up. Okay, and so yes, so let's look. So okay, what is a prime implicant? Well, let's go back to this map. If we looked at every single one by itself is an implicant, and you could also say that, I guess, about the zeros, but we normally don't. We normally, when we talk about prime implicants, we're usually talking about the minterm solution, the SOP solution. All right, so this box alone is an implicant, but it's not prime because this box of 1 can be combined with another box of 1 to make a group of 2. Therefore, it's not prime. Now we have a group of 2. Is that group of 2 prime? Yes, that group of 2 is prime because it cannot be combined with another group of 2 to make a group of 4. There is no group of 4 here. Now, if we look back at let's see, did we have a group of 4 someplace? Thought I did. No, not there. Not there. Not there either. Okay. Oh, here. Okay, here we have a group of here we do have some groups of 4. Okay, you can see a group of 4 up here. You can see a group of 4 down here, and you can see a whole column group of 4 here. So notice, if you just took this group of 2 and you ask, is this prime? what that question implies is, could you combine this group of these two boxes grouped together to another group of 2 to make a group of 4? Well, yes, you can, because here's another group of 2 boxes, and they exactly can combine here to make a group of 4, because they each differ by their partner box by a single variable. All right, so you can also go about it another way. You can say, what if you had this group of 2 here? Is it prime? No, it's not prime, because you can combine it with this group of 2 to make a group of 4. So we have implicants, we have prime implicants, and then of the prime implicants, we have some essential and non-essential. Now, how do we tell if they're essential? Okay, go back to this one. So the two red groups are essential, but how do we know that? Well, when we draw in the blue box, what we see is that in the blue box, we see that in the red groups, we see that there's one in this group that is not covered. That's the A prime, B prime, C prime term. The top one is not covered by any other groups. And we see in the A prime, B, D term, the other red loop, that the bottom one is not covered with any other prime implicant. But the blue dashed line encloses 2 1s, and in those 2 1s, we definitely see that those other 2 terms we just looked at cover both of the ones in that group. So that's why that blue one's not essential. It doesn't cover any additional ones that haven't already been covered. And so that's why we call the red loops essential and the blue loop non-essential, or a consensus term. But they're all 3 prime implicants because they cannot be combined with another group of 2 to make a group of 4. There's no group of 4 on this map. All right. So here we have a number of things to look at. Let's look at it. So we could do these 2, but do you see another group of 2 that we could combine this group of 2 with to make a group of 4? Yeah, you combine that group of 2 with the first group of 2, and we get the whole column. What about here? Yes, you can combine that group of 2 with that group of 2 to make the group of 4. And you combine, same thing here. You combine this group of 2 with that group of 2 to make a group of 4, the top 2 with the bottom 2 to make a group of 4, and then we have this whole column. Now, when we add this vertical column, which is going to be AB because of the 2 1s up here at the top, that whole column, are there any ones in this whole column that are not already covered by another prime implicant? And the answer is no. The top 2 1s are covered by the group of 4 on top, and the bottom 2 1s are covered by the group of 4 to the right on the bottom. So therefore, there's no new ones being covered. They're all already being taken care of. So this group of 4 in this column becomes a non-essential prime implicant. It is prime because it cannot be combined with another group of 4. There's no other column with all 4 1s covered, with all 4 1s present, that you can combine it with to get a group of 8. But it is a legitimate group of 4. It's just not essential. It's non-essential. Now, what other prime implicants do you see? Well, most people would see most people would see this group of 2 here. But what they might not see is this wraparound group. And they probably would see that. But this is the one that's more obvious. Now, how many of these, all these are prime implicants. Some of them are non-essential. Now you'll notice that this group of 2 here, this vertical group of 2 on these 1s in the first column, that prime implicant that covers those 2 only covers ones that are covered by other prime implicants. So it's non-essential. But when you want to pick the best solution, that's what you get. So clearly this group of 2 over here on the left column is the best choice, but it's not essential because you can cover those ones other ways. But the 2 groups of 4, there are ones in those groups that are not covered by any other groups. If you look at this, and now again, notice that the upper left-hand corner one in the top group of 4, and the bottom right-hand column one in the bottom group of 4 is all by itself, not covered by any other prime implicant. So if you didn't include those square groups of 4, you would miss those 2 ones, one in each of those groups. That's what makes them essential. Okay. And even though these other ones are legitimate prime implicants and also non-essential, they wouldn't be your first choice for covering all the ones, and you would probably consider those as consensus terms. But if you had both of those terms in your solution, then this one would be considered. Then the vertical group of 2 in the first column would be considered a consensus term. So whether or not you think of it as a consensus term depends somewhat on how you pick your solution. Same with this. So you might have to add those consensus terms to fix the hazard, but you don't need them. You don't need them if you don't have a problem with the hazard to cover all the ones to give you a legitimate solution. All right. What about this group? How many prime implicants do you see? Test yourself. Pause the video and see if you can figure it out. All right. Okay, assume you took a few seconds to try and figure it out. So most people obviously see this group of 4. And then most people see that group of 2 and that group of 2. But what other ones exist? Well, there's a wraparound group like that, and there's also a wraparound group like that. So if you didn't see all of those, so what you get here then is we have one group of 4, and we have 1, 2, 3, 4 groups of 2. So you have all totaled 5 prime implicants on this map. Those are all prime, but some of them are non-essential. And the ones that are non-essential are where ones are being covered by, where all the ones in the group are covered by other groups. And it turns out you have 2 of the groups of 2 are essential, and 2 of the groups of 2 are non-essential. But to get a solution, to get that one in box 0, the upper left-hand corner box, you have to have one of the non-essentials chosen in your solution. And then the other one becomes a consensus term, depending on which one you chose. All right. So, okay, I think this covers most of it. Now, what if you go with 5 variables? How does this work? Well, so one way to do it is to put a dash line in all the boxes, but this is terribly confusing. And then you have AB across the top, CD down the side, and you have E in a 1-0 configuration. So E and E prime. So this bottom box here would be A prime, B prime, C prime, D prime, E prime. And this top little square in this upper right-hand corner box, this top triangle, the upper left triangle in that upper left box would be A prime, B prime, C prime, D prime, E. Okay? So that's how we often do it. Or you can reverse the 1 and the 0 if you like that better. All right, but this is a terribly clumsy way to do it. What you're really doing is you're doing this 3-dimensional visualization. A much better way to do it. So you see this one would be A prime, B prime, C prime, D prime, E, whereas this box here would be A prime, C prime, A prime, B prime, C prime, D prime, E prime. It'd be all primes. Like we see here, 0, 0, 0, whereas this one's 0, 0, 0, 0, 1. All right. This is cumbersome, though, because you can't really see into this cube. You can't write it on paper, so it doesn't really work. So what do we actually do? What we actually do is we make 2 4-variable maps. Let's see, did I do that? I didn't do that. Yeah, we do 2 of these maps, and then so let me show you on paper. Yeah. Okay, so we make 2. So we're going to do a 5-variable. Let's say, I'm just going to plot a few terms, but let's say we have f of A, B, C, D, E. And it's going to, let's say it equals the sum of the min terms, little m, and now we're going to do the notation. We'll do term 0, 1, and 3. Okay, something like that. All right, so we would create a map here, and what would that be? So this would be A prime, B prime, C prime, D prime, E prime, and then the one term would be A prime, B prime, C prime, D prime, D prime, E, and then the 3 would be A prime, B prime, C prime, D, E. Okay? So that's what those terms would be. Well, let's draw the map. So we have two maps. Okay, like that. Two 4-variable maps. And we set them up. Now there's a couple different ways you can do this. A bunch of different ways. But you pick one of your variables, and you generally have some rationale for why you picked it. If you don't have any rationale, then maybe you just pick the higher order variable. So we'll call this map BCDE, and we'll say this is where A equals 0 for this whole map. And over here we'll say this is A equals 1, but the top row is BC and DE. Or you could pick the E variable, and then you could have this could be ABCD with E equals 0, and this could be ABCD with E equals 1. So it doesn't matter how you pick it, but this is how you do it. So let's plot these in this crazy map. So since this is all A0, where A prime, so this one would be a 1 right here. That would be A prime, B prime, C prime, D prime, E prime. And then if we want to be A prime, B prime, C prime, D prime, E, which is this one, minterm 1, that would just simply be there. And then if we have minterm 3, then that's going to be down here. So the way this works, remember, if you have 2 to the 5, so you have 5 variables, so that's 32. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we normally number them 0, 1, we flip the rows, 2, 3, 4, 5, 6, 7, 8, 9, well, I'm not going to do that. I'm going to do 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. We left out a column. Man, oh man. So 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and 31. Okay? And because we start with 0, we wind up with 0 to 31 and not 1 to 32. Okay, and that's how these things line up. So you can figure out which terms you have. So if we also had midterm, say 27, then we'd have to put a 1 here. Okay. Now, if you also had, say, midterm 11 here, you could combine these. You could kind of do a little loop-de-loop like that, or you can use colors or other ways to do it. So this is the way to do a 5-variable map. A 6-variable map is crazy, and I'm not even going to ask you about a 5-variable map, but we're not even going to do anything to do with 6 variables. Once you get past 5 variables in the K-map world, you're kind of done. It's better to go get a computer-based tool and use the computer-based tool, machine calculated. All right. Okay. All right. So let's go back to the book here, and then to the slides rather. There's other things we can do with K-maps. We can, let's say we wanted to do a POS to SOP conversion, or So let's do POS to SOP. All right. So here it is. I'm just going to make one up. Or maybe I should do one from the test. I don't know. All right. So let me go back to the paper. And okay. So here we go. So I'm going to do a K-map, and then I'm just going to come up with an arbitrary function, and we're going to convert it. Maybe what I'll do, actually, let me escape. I'm going to go back to the previous set of slides, and I'm going to pick, let's see, I guess we had K. So, so 5, yeah, and we had, no, okay, sorry. All right, let me. Okay, let's do one that's kind of tricky here. I could do the last one, but that's got too many variables. So let's do B. It's not entirely obvious how easy that is, but anyway, well, yeah, it's pretty easy. But let's do it. Okay, so I'm going to do that one. Sorry, oh, you can't even see that. My bad. Okay, transition. Okay, so we're going to do, you know what, let's do one of these. I actually know these are crazy bad. So I'm going to do E. K, so let me write this down, and then I'll do this with I think it's just 4 variables. Let me just check. So K plus L plus M. Quantity times K plus M plus N. K prime plus L prime plus M prime. And finally, K prime, L prime, M prime, K prime, yeah, K plus M plus N. K prime plus L prime plus M prime. And finally, K prime plus M prime plus N prime. Yeah. K prime plus M prime plus N prime. Okay. N prime. All right, we got it written down. Now let's transition over here. All right. Okay, so first I'm going to switch this to A, B, C, D. And we just have K, L, M, N. Yeah, so that's good. All right, and I'm going to put on my glasses so I can see a little better. So K, L, M, N just equals A, B, C, D. Okay, so this is going to be A plus B plus C times A plus B plus D times A prime plus B prime plus C prime times A prime plus C prime plus D prime. Okay, so all I did was let K, L, M, and N be A, B, C, D. And that's because I really like to use A, B, C, D, because I make fewer mistakes if I do A, B, C, D, and I can switch it back. All right, so I want to make this go to POS. And the way I do this is very simple. I plot every one of these terms, and then I just flip them. Now, because these are POS, it's POS form, I'm going to invert them and plot them as though they were ones, but I'm going to write zeros instead because that's what they actually are. So if I take the first term and I invert that, A, B, C, I'm going to get A prime, B prime, C prime plus, well, no, I'm just going to write that there. So that would be A prime, B prime, C prime. So A prime, B prime is this whole column. C prime would be these two because D dropped. And D is prime here and D is not prime there, so D drops. So it would be 2 ones right there. But since it's actually zeros, I'm going to put zeros instead. So when I convert it from the SOP to the POS form, from the POS to the SOP form, from the max term to the min term, then I know I can plot it as if it were a min term, and I would plot ones if it really were a min term, but it's not. It's a max term, so I'm plotting zeros. It just helps me do it without making mistakes. You don't have to do it this way. And then we have ABD, so that's just going to be A prime, B prime, D prime, and so A prime, B prime, D prime would be these two boxes, this one up here and this one down here, because the AB prime is this whole column, but D prime are the bottom row and top row. But I don't plot ones, I plot zeros. And I already have a 0 there, so I don't have to do any more. Okay, then this one, so that's going to be A, B, C, A, B, C. So I know these two columns are A, this column is A, B, and C is the bottom two, so it's going to be here. Here, they would be 1s, but it's not. It's actually a max term, so I'm going to plot 0s. Okay, and then I can erase these. I can scratch these out because I don't want to confuse myself or anybody looking at this thinking I didn't know what I was doing. And then here we have A prime, C prime, D prime. So that's just going to be A, C, D. All right. So A. So the B drops. So it looks like it's going to be the whole 2A column, the 2A columns here, and then the two bottom C rows. And then since it's just D, it's just going to be these two zeros here. Now I always know if only one variable drops, it's a two variable term. Did I did something wrong with this. Let's see. This was A, B, C. Oh yeah, A, B, C. Right. Okay, never mind. So these overlap. All right. Now once I've got this, I plotted all the zeros. I plotted all these max terms by inverting them, pretending they're 1s, inverting them, but really writing zeros instead of the 1s. Okay? Now I'm going to put in the 1s. Now, so there's some things that are obvious. So this whole column is obvious. This group of 4 is obvious. There's another group of 4, though, right here. Looks like we probably won't need that group of 4. And then there's a group of 2 here, and there's a wraparound group of 1, a group of 2 there. So I have 1, 2, 3 groups of 4, and 1, 2 groups of 2. But what do I actually need for the solution? I need this group of 2, this whole column, that group of 4. I need this group of 4 here in a block, and I need this group. So I don't need this group of 4 right there. I can leave that out because those ones are all covered by other loops. So that's a consensus term, makes it a non-essential prime implicant. But I have 1, 2, 3, 4, in the group, and 5. So I have 5 prime implicants. Of which 1, 2, 3, 4 are essential. 4 essential PIs, prime implicants, and 1 non-essential PI. Okay, now, so my final solution then would, so let's write out the conversion. So what is the SOP form? The SOP form then, can't even write, SOP equals, so it's going to equal this group of 4, which is A prime B, plus this group of 4, which is A, C, and this group of 2, which is A prime C, D, and this group of 2, which is A, B prime, D prime. So AB, AC, A prime C, D, A, B prime, D prime. And I know that's in simplest form. There's nothing, I cannot reduce that anymore. And it turns out it's quite a lot of work. It's a lot of work to get from this to that, or from that back to this. So it's a lot easier if I put it in the K-map and do it that way. So that's a real handy way to go from SOP to POS. All right. So let me, let's see. Yeah. Okay. So I have now covered pretty much everything I wanted to cover on K-maps, but what needs to happen now, you need to do practice, and you need to practice reading, plotting terms, both min terms and max terms, and reading off zeros, groups of zeros and groups of 1. Now, one thing that students often mess up is they forget the golden rule, and the golden rule is only powers of 2, which means one box all by itself, a group of 2 boxes, a group of 4 boxes, a group of 8 boxes, and then obviously if you have a really big map, if you're doing a 5 variable thing, you could have 16 boxes maybe, but normally really just groups of 1, groups of 2 boxes, groups of 4, and rarely groups of 8. That's it. Do not try and group groups of 3 or groups of 5 or 6 or 7 or 10 or 9 or 12. Those are not legal. They have to be powers of 2, and 1 is a power of 2 because that's 2 to the 0, and then 2 to the 1 is 2, 2 to the 2 is 4, and 2 to the 3 is 8. And probably you almost never have 16 boxes. We will maybe frequently see that actually in some situations where everything in the whole map is a 4 variable map, and every box has a 1 in it, or every box has a 0 in it. So there you could have a group of 16 where you drop all your variables and you just have a constant for a 4 variable map. Okay? All right, hopefully that makes good sense. Now let's take a quick look at Unit 7, and then we'll finish up Unit 7 then on Monday's video, which actually is, I think it's already Monday, but I'll do the video later today for Monday. All right, so let me just quickly go to that. Hang on. Okay, so let's go to Chapter 7 in the book. So the first thing, what we're going to see is this is basically kind of the summary of, a little bit of a summary of combinational design. So remember, we have some inputs and we have some outputs, maybe one, maybe multiple on both sides. It could be multiple outputs and one input, could be multiple inputs and one output, could be multiple inputs and multiple outputs. So you can think of this as a switch that puts in a 3-bit value, say in this case 0, 1, 2, 3, 4, 5, 6, or 7, and then the network generates this 7-segment display of the digit. So that'd be an example, and you're going to do some things very similar to that. So it's actually a pretty good example. Now, so what's happening here? I want you to. I want you to be able to list out the major steps in a simple combinational design. So in our combinational world, we have an input, and once we have it sends in some number of bits into this network, and we get some number of bits out, and the bits going in absolutely determine exactly what comes out, because there's no history, no memory inside the network. And once we change what's going in, we have to wait just a small propagation delay, and then these outputs will stay the same until the input changes. And if we go back to the original input, we should get the same thing out that we got before. It should be completely deterministic. All right, so you should list the steps in how we do this. We're going to go over those. You should describe at least a couple different ways of simplifying a combinational design from its truth table, and we've covered switching algebra, and we've covered K-maps, so you can use either one of those tools. And then you should be able to explain why the don't cares can arise in a combinational design, and how they can help you with simplification. And finally, you should be able to describe how to realize the design in hardware in both and networks. And for that matter, I also want you to be able to change the and/or to a NAND, and change the or/and to a NOR. And we'll talk about that as well. Okay, so we have this concept of combinational design, and we're going to define that. Propagation delay, or a term that we use in Verilog, is inertial delay. And so it's probably better if you use the term inertial delay. And then there are 2-level networks, so we have theoretically a set of input gates and one output gate. That would be a typical 2-level network. And then we have some number of inputs and some number of outputs. And you should read through these definitions and make sure you understand them. Here's a video for chapter 7. You should definitely watch that. It just will add information. There is some repetition. And then we have this general approach. So here's kind of the steps. So first we define the inputs, which are the independent variables. Let's say you have n inputs, okay? And then we define all our desired outputs. How many outputs do we have, and what values do we want for each set of inputs? And sometimes we'll refer to that as M outputs. So we have N inputs and M outputs. N could be bigger than M, or it could be smaller. And then we construct a truth table. So because we have N independent variables, it's going to have 2 to the n rows. And it's going to have a column for every one of our independent variables and also every one of our outputs. So that's M plus N columns. So it's going to be 2 to the n rows by M plus N columns. And then we want to talk about what the form of the desired solution is going to be from our truth table. So are we going to create an and/or network with some inverters, perhaps? Are we going to create a or/and network? Or are we going to create a NAND network or a NOR? Now there's 4 other forms which we haven't really discussed, but they just don't occur that frequently. But you'll see. We'll talk about them here in just a little bit. Okay. And then finally, we minimize the logic expression. And then finally, we can enter the design in a hardware description language, which we haven't defined yet, but we will. Or we can draw a schematic and start building it from discrete components. But if we use hardware description language, you can use that language to have a fancy piece of software generate all of the photomasks and steps in the Foundry to make the integrated circuit, or we can have it generate a bit file, which will then program into a programmable hardware device like an FPGA or a CPLD, which stands for Field Programmable Gate Array. So those are the really big chips, or a complex programmable CPGA, complex programmable gate array. So we often, if we have a smaller project, then we may not use the FPGA, but if we have a big product, the FPGAs tend to be a lot bigger than the CPLDs. Okay. So although it's called complex logic device, it's actually pretty simple. So CPLD versus FPGA. There are smaller programmable logic that we can use, but it's kind of falling by the wayside because we generally are going to use an FPGA or a CPLD or maybe a microprocessor to do it all for us, or sometimes both. But the smaller logic is gone away because it normally doesn't use our hardware description language. Okay, we're going to, I think coming right up, we're going to talk about hardware description languages, but we haven't gotten to that yet, so you just have to hang tight. All right, again, here's our standard inputs and an output. In this case, we have 3 inputs, A, B, C, 1 output, F. And where do we get the output from? We get it from God, right? It's given to us. So in this case, we have a 0 for our first row, a 0 for our next row, a 0 for our next, and a 0 for the next, and a 0 for the next. So if we wrote out the max term notation, and let me do that real quick. Let's see. What I want to do is, yeah, let's do that. So flip this out. So we have, turns out in this case, so F equals okay, I'll do the min term notation. So it turns out we have min terms, little m's, 5, 6, 7. And for the max terms, we have F equals the product of the big M's, and that would be 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Now, we can write these out, and we can simplify them in switching algebra, or we can do a K-map. It's a lot easier to do a K-map. So let's do a 3-variable K-map, and we can simplify it right off the bat with our K-map. And we see what this looks like. Okay, we'll do ABC, or we'll do A at the top and BC down the side. And then, so I'll label them 0, 1, 2, 3, 4, 5, 6, 7. Remember, I had to flip the bottom 2 rows. But it's a 3-variable map, so I don't have to flip any columns because I just have 1 variable across the top. All right, now I'm going to plot 5, 6, and 7. So that gives you one group of 2 here and one group of 2 here. What about the zeros? The zeros are a little nicer. So you have a 0, 0, 0, 0, and 0. So you group those 2 and that group of 4. So this group of 4 is going to be A prime, but you have to invert it because it's actually a 0. So it's just going to be A. And this group of 2 would be B prime, C prime, but you invert that, it's B plus C. So that times A equals the max term, or POS. And then if you do these, we have A, C plus A, B. So AC plus AB. So that is our equals SOP. Now, if we look at this, we realize we could have easily used switching algebra, just distribute that in, and you get AB plus AC, which is exactly what we have here. So we could have used switching algebra pretty easily in this problem, but the K-map can often really help us too, and it's a good double check. And then in some cases it helps us a lot, especially in 4-variable problems and where you got a bunch of terms floating around. All right, so that's how we do that. Let's just let's see. Yeah. Sorry. Okay. Yeah. Yeah. That's what I want. Okay. So So going on down. So you hear there's the there's our SOP expression, and we can simplify it. We can combine ABC prime with ABC and get AB. We can get A prime, B prime, C with ABC and get AC. And that gives us AC plus AB. Boom. And then you can factor out the A times B plus C. That's easy. So it's in POS. Here's the K-map. So you can see we get these 2 circles with the 1s, and then if you want to do the zeros, just what I did, where we circle this whole column in the top row, and that gives us 2 terms, and that's the B times it's the A times B plus C. All right, and here are the circuits. This is our A times B plus C. That's the POS form, and here's the SOP, AB plus AC. Okay, and that's it. So we talked about our functional 2 layers. So I did want to point out a couple of things here that, and this comes right out of the book. We have the slides too, but so we have if you take OR, AND, NAND, and NOR, you can make 16 different 2-layer networks with those 4 gates. Okay, but of those, let's see, the ones that are starred. Let's see, the ones that are starred will implement any logic expression and it'll implement it in 2 layers. But the ones that don't have asterisks on them cannot implement any logic expression. In fact, they typically simplify down to just an OR gate, or just an AND gate, or just a NAND gate, or just a NOR gate, and that's not capable. A single one gate isn't sufficient to implement any logic expression. It takes one of these combinations. Now note, we've talked about, in this case, we've talked about AND, OR, and we've talked about NAND, and NOR. But there are a couple of others. There is a NAND AND, there is a NOR OR, there is an OR NAND, and an AND NOR. So all told, there are 8 functionally complete gate sets out of this group of gates, and there are 8 that are not functionally complete. And again, the ones with the stars are the functionally complete ones. But the only ones I want you to worry about, and let me just do that right now. The only ones I really want you to worry about, I want you to worry about and, or, and nan, NAND. Or I want you to worry about or and nor. And it turns out nan, and nor are often what we build devices with. And the reason is we want, if we're going to build an integrated circuit, we want all our transistors on the integrated circuit to be as identical as they can be. And when you fabricate them, you fabricate the whole chip all at once, and it turns out that it works pretty well. You get very uniform creation of equivalent transistors. But if you set it up as an and or, now you got to make and gates and or gates, and so you might find yourself having to make slightly different transistors for the and gates to make them efficient, and then the or gates, and so then you wind up with gates that have maybe various propagation delays. Whereas if they're all NAND gates or they're all NOR gates, then they're going to be a lot more uniform. Maybe they'll all have the very similar propagation delays. So that's one of the reasons why we tend to want to have all the same gates as much as possible. Now, in any fancy big chip, there's all sorts of stuff going on. But still, if we have gates, they're going to be implemented in the same way. All right. Okay, so I think that's really pretty much what I wanted to cover. Let's see, do this one more time. So yeah, this shows you the groups. We can work around this circle using switching algebra, or we can do it graphically using our using these alternative symbols. Well, these aren't the alternative symbols. Sorry, these are what our gates look like if we represent them. That's an AND gate. That's an AND gate. Notice the tick out here. That's an OR gate. That's an OR gate. That's how they look when we write them as equations. And yeah, so here are alternative labels. So notice an AND gate can be subbed out for an OR gate with bubbles on the inputs and a bubble on the output. A NAND gate, though, it just has bubbles in the input. So the way you can remember this is you take any one of these gates, AND, NAND, OR, or NOR, and you can substitute them with the alternative gate. So you swap the gate. So if you have an OR gate, now you put an AND gate in, and then you take all the bubbles and you flip them. So if there are no bubbles on the inputs, you put bubbles on the inputs. But if there is a bubble on the output, then you take it off. If there's no bubble on the output, then you add it. And so that's why this winds up to be an OR gate with bubbles on the input and the output. But this winds up to be just bubbles on the input because you have a bubble there, so you take it off. And same here. The standard OR gate, bubbles on the inputs, bubble on the output of the AND gate. But here, you sub in an AND gate and you take the bubble off the output because you flip it, but you put the bubbles on the input. And oftentimes we can do this graphically. We can slide the bubbles up the wires, and it works out great. So for instance, I'll show you this real quick, and I think I'm going to quit on this. So let's say we have, and maybe I have it here. No, I don't. So let me go back to one of these we did before, maybe something like this. Yeah, let's say we have this right here, this circuit, AC going into an AND gate and then into the output OR gate, AB. So that's AC times plus AB, AC plus AB. Okay, so let's do that. F equals AC plus AB. So let me draw this out. Okay, so I have this equation, and I have AC and AB, and they both go into an OR gate, and that's my F coming out. Now, all I have to do to swap this out is I take an AND gate and I pop it in here, and I put bubbles on the inputs and the outputs. So that's my alternative symbol for this OR gate. Bubbles on everything that didn't have bubbles has bubbles now. And then I take these bubbles and I slide them up the wire, and they go here. And now they come off of here. So now I just have a wire connecting these and a wire connecting these. There's no bubbles on the inputs, so the bubbles here. And now I have a NAND gate a NAND gate, and a NAND gate. So I've now implemented it using a graphical technique to get NAND gate and NAND gate. What if I wanted to do switching algebra technique? Well, so I write it AB plus AC equals F. Okay, now I just doubly invert it and partially expand it. So I bring this in, and then I'm going to have AB with a tick. I'm going to get rid of the plus, so it's going to be a times, and I'm going to have AC with a tick. And then the whole thing's going to have a tick. So if I go back to, where it makes, let's see, where did I do it? So I want to, here. So notice that's an AND, that's an AND. So I have in parentheses with a tick. And then in this case, notice that's a NAND because it's got a tick on it, and it's A times B. And this is AC with a tick, so that's a NAND. And then this whole thing is you could call this XY with a tick. And that's another NAND. So this is a NAND. And it looks just like this. That's what it would look like. Bubbles on the outputs and 3 AND gates. No bubbles on the inputs. Okay? Done. All right, so let me go back to here. All right, so hopefully you're getting a good taste. Go ahead and be sure and look at the videos for Chapter 6 and 7 if you haven't done that. Get ready to do the end of chapter quizzes. Make sure you check the dates in the syllabus for those. And then we're going to work a little more on 7, and we're going to talk about 8 coming up real soon. So we're just going to keep cruising through, and we are going to get a little taste of our Verilog hardware description language in this group. So remember, 3 big parts. We've already finished the first third of the course. We're in the middle third now. The first third was binary, Boolean algebra, binary arithmetic, our theorems, conversion from SOP to POS and vice versa using switching algebra, truth tables, and how to write min-term and max-term expressions from a truth table. And then we threw in a few other things like codes, fault-tolerant codes, gray codes, codes that can be used for computing values. And then we looked at design by iteration to take 4 1-bit adders and daisy chain them together to make a 4-bit adder. So that's pretty much what we covered in the first part. Now in this part we're fleshing out the whole concept of combinational design using a truth table that you get from your customer essentially, and converting that into a simplified logic expression and implementing it, say, in whatever hardware form you want, SOP, NAND, POS, NOR. Maybe those 4. Remembering there are 4 others, but we don't really use those much. So I'm not going to test you on them. I just want you to be aware of them. And you can see them in this, let's see, where is it? It's, you can see that in this chart here. So there would be like, obviously OR AND is SOP, POS rather, but there is an OR NAND, we don't use that much, and there is a AND NOR, we don't use that much, but AND OR is SOP. And then there's NAND AND, we don't use that much, but NAND we do, and there's NOR OR, we don't use that much, but NOR we use a lot. So those are, and also when you make a NOR gate or a NAND gate, it takes fewer transistors than an OR gate and an AND gate for all intents and purposes. All right. Okay, so that pretty much concludes what I wanted to cover. This was the video for Friday. I will record one for Monday, but it'll be done a little bit later. And I'll also send out an email letting you know this one's finally been posted. All right, and that will be the end of this.